Hello everyone. Welcome to AskPrep. My name is Gaganavi. In today's class, we'll study about the chapter 2, that is structure of atom continuation. In the previous class, we studied the different spectral lines and all. So we'll continue with the spectral series of hydrogen spectrum. Spectral series of hydrogen spectrum. The spectral lines arise from the transition of electron from a spectral series. So, how an electron is excited from the ground state to the excited state, it indicates the formation of the line, that is the spectrum. And there are 5 different series, and each different series are named with the respective their discoverer scientist. So the first scientist is Lyman, Balmer, Paschen, Brackett, and Fund. So correspondingly, all these are named with the name of the series. So, according to Bohr's theory, the wavelength of the radiations emitted from hydrogen atom is given by 1 by lambda, which is equal to R multiplied by 1 by n1 square minus 1 by n2 square. This is the formula to find out the wavelength of the radiations emitted from the spectra. So, this is the formula. And n2 is the outer orbit, n1 is the inner orbit here. That is the we have to measure the distance between the orbits. So n1 and n2 is taken. So this is the transitions or the spectral lines occurring in the hydrogen atom, the hydrogen spectra. This Lyman series, Balmer, Paschen, Brackett, and Fund. This is the ground state, that it is taken as n1, that is n equals to 1. It is from, see, we can correspondingly see how many lines are possible up to the infinity, n is equals to infinity. And this is the Balmer series. Up here, the level starts, or the orbit length starts from n is equal to 2. N is equals to 1 is Lyman, n is equals to 2 is Balmer, and Paschen, n is equals to 3. The starting exciting level of the orbit is the third orbit. Here first, second, third, fourth, fifth, it continue up to 5. So the electron excitation start from those number of orbits it takes place. So the next one, the first one is Lyman series. So the lines corresponding to transition from outer energy levels n2, that is 2, 3, 4 to first orbit n1 is constitute Lyman series. So here what happens? N2 is the outer energy level. So n1 is the first orbit, that is the inner orbit. n1 is 1 and n2 is 2. Up to infinity it can occur. So we have to substitute the help of this formula so that you will get the number of electrons transmitted. It is so this series of Lyman series electron lies in the ultraviolet region of the spectrum. So in ultraviolet region of the electromagnetic spectrum, we can observe Lyman series, and we have to take as n is equals to 1 and n is equals to 2 and 2. That is n2 is equals to 2 and 1 is equals to 1. So the next is Balmer series. See the lines corresponding for transition from n2 is 3, 4, 5. The orbit, it is according to the series, the n1 and n2 value goes on increasing. So in Lyman it is n2 is 2, 3, 4, 5. Here it is 3, 4, 5. n1 is 2. There n1 is 1. If these values are given, or if they are given Balmer series, you have to substitute with the help of these starting as N1 as 2 and N2 as 3, like that. So the wave number of different lines are given by, so this is the wavelength reciprocal. Wave number is reciprocal of the wavelength. So 1 by lambda is equals to R 1 by 2 square, as N1 is 2 minus N2 square. It may be 3, 4, 5, any number of transitions. And this Balmer series lies in the visible region of electromagnetic spectrum, and this series is only obtained in emission spectrum. So the next is Paschen series. See, again, line corresponding to N2 is 4, 5, 6, N1 is 3, it constitutes Paschen series. And the wave numbers of different lines are given by R, that is wave number nu bar 1 by 3 square minus 1 by N2 square. So this lies in the infrared region of the electromagnetic spectrum. This is also obtained in emission spectra. So the next is bracket series. So the series corresponding to transitions, that is N2 is 5, 6, 7, N1 is 4. The wave numbers are given series. It lies in the infrared region of the electromagnetic spectrum. Fund series. So this is the same. N2 is 6, 7, 8, N1 is 5. So always it is a number preceding. The wave number is given by mu bar is equal to R 1 by 5 square minus 1 by N2 square. So in problems and all, if they ask the electron transition takes place from this orbit to this orbit. So this is the orbit, outer orbit to inner orbit. How many are from inner orbit to outer orbit? If they give the series, if it is fund or bracket or Paschen, you have to know where the N1 and N2 value. So it is already given, and you have to substitute those values in this formula. And it is also lying in infrared region. So the next concept is Bohr's postulates for hydrogen atom. So Bohr proposed few postulates upon his assumption for an hydrogen atom. So how does a hydrogen atom electron move? It moves around the nucleus in a circular path of fixed radius and energy. So Bohr orbit hydrogen atom has fixed radius and energy. And these paths are called orbits or stationary states. So these, as it is a circular path and any circle do not have an end point. So it is a stationary, it is allowing to revolve in the same axis. And these orbits are arranged concentrically around the nucleus. See, around the nucleus there are orbits present which are revolving, which contains electrons which are revolving in those orbits. And these energy of an electron do not change with time. So as time increases, the energy remains constant in an electron. The electron moves from lower stationary state to higher stationary state. So it cannot move at a very lesser distance. So from always it moves from lower to higher. It has to absorb the energy required to move from lower to higher, and it absorbs the energy emitted when it moves to higher region. The frequency of the radiation absorbed or emitted when transition occurs between two stationary states that differ in the energy by delta E is given by N is equal to delta E by H. Delta E is E2 minus E1, that is energy of lower minus the energy of the higher by H. E1 is lower and E2 is higher energy states. And this is called the Bohr frequency rule. So this is how when energy is absorbed or when a transition occurs, Bohr stated this frequency at which the electron can absorb or transmit the energy or it undergoes transition. And for movement of an electron, angular momentum is required. So this angular momentum is always a quantized quantity, and it is stationary state. It is present in the stationary state, or electron is always present in the stationary state. And it is given by the expression m, mass of the electron, Vr is equal to nh by 2 pi, where n is equal to 1, 2 and 3, where me is the mass of the electron, v is the velocity, and r is the radius of the orbit where the electron is moving. So, based upon the postulates, he proposed the theory for the hydrogen atom. So, the stationary states for electron are numbered as n is equal to 1, 2 and 3. These numbers are known as principal quantum numbers. So, we have to give a number to an electron with the stationary state. So, this is labeled as 1, 2 and 3. And so electron has some radii. And this is expressed as Rn is equal to n square A naught, where A naught is equal to 52.9 picometer. So, the radius of the first stationary state is called Bohr orbit. So, as Bohr proposed the radius of the stationary state, the first orbit is called Bohr orbit, which is 52.9 picometer. Normally, the electron in the hydrogen atom is found in this orbit, that is n is equal to 1. As the value of n increases, the value of r will also increase. If the principal quantum number increase, obviously the radius of the electron is also increasing, because as the number of shells increases, more the radius of the, more the number of electrons, more the occupancy, and the radius is bigger. So electron moves away from the nucleus. If the n value is more, electron starts moving away. And the most important property which is associated with the electron is the energy of its stationary state. So, energy which is present in an electron is given by a stationary state, and that is given by the expression E is equals to minus RH, that is 1 by n square, where n is equals to 1, 2 and 3. It is the stationary states, that is 1, 2, 3 principal quantum numbers. Here RH is called the Rydberg constant, and this was proposed by the scientist Rydberg, and its value is 2.18 into 10 power minus 18 joules. And the energy of the lowest state, that is the ground state or the Bohr's orbit, as the radius ground state is called E1, that is minus 2.18 into 10 power minus 18, 1 by 1 square. So it is the same. The energy of the stationary state for n is equals to 2, that is E2 is equal to minus 2.18 into 10 power minus 18 joules, 1 by 2 square, that is 0.545 into 10 power minus 18 joules. And this Bohr theory, not only for hydrogen atom, it can also be applied to the ions containing only one electron. For example, helium, lithium, beryllium, and so on. And the energies of the stationary state associated with these kinds of ions is known as the hydrogen-like species is given by the expression En is equals to minus 2.18 into 10 power minus 18, and radii is given by the expression Rn is equals to 52.9 into n, that is the principal quantum number, by Z picometer. So we can also calculate the velocities of the electrons moving. So with the help of the angular momentum, we can calculate the velocities. So the velocity of the electron increases with the increase in the positive charge of the nucleus. So as more and more the nucleus becomes positively charged, the velocity of the electron also increases, and it decreases with the increase of principal quantum number. As the number of shells increases, velocity decreases. As the number of positive charge increases in the nuclei, velocity increases. So for helium and lithium ions, the value is 2 and 3 because the number of ions are 2 and 3. So from the above equation, we can conclude that the value of energy becomes more negative and that of radius becomes more smaller in this case. And that is why as energy becomes more negative, the electrons are very tightly bound to the nucleus and are tightly held. So then what are the limitations of Bohr's model of hydrogen atom? So it fails to account for the finer details. That is, if the doublet in the sense if two lines are closely spaced in the hydrogen spectrum, by using the spectroscopic techniques, can identify that. So he was not able to explain for other atoms like helium, which possess only 2 electrons. He could explain for 1 electron, but he couldn't explain for 2 electron, that is helium atom. So this was a failure. And he couldn't explain about the splitting of spectral lines in presence of magnetic field. So how the spectral lines get splitted in presence of magnetic field, Zeeman effect or an electric effect. This is called if the splitting takes place in presence of magnetic field, it is called Zeeman effect. And if the splitting of electron takes place or the spectral line splitting takes place in presence of electric field, it is called Stark effect. So he couldn't explain in both the magnetic and electric fields. And the formation of the molecules also he couldn't explain. How an atom forms a molecule by forming a chemical bond, he couldn't explain that. And he also concluded that electron is a charged particle. It moves in a circular orbits around the nucleus. But the wave nature or the wave character of the electron is not considered in the Bohr model. In Bohr model, it could not be considered. And it could explain for only hydrogen atom, and no other atom satisfied this Bohr condition. And therefore, Bohr model of the hydrogen, it not only ignores the dual behavior of matter, and it also couldn't explain the Heisenberg uncertainty principle. So the next concept is about dual behavior of matter. De Broglie in the year 1924 proposed that matter like radiation exhibit dual behavior, that is both particle and wave-like properties. So what does that mean? Photon has both momentum as well as wavelength. Electrons also have momentum as well as wavelength. So de Broglie, from the relation he gave, lambda, that is wavelength, is equals to h by mv, or momentum is mv, that is p is momentum. So p is equals to mv. He given lambda is equals to h by p. Here, where m is the mass of the particle, v is the velocity, and p is the momentum. So, de Broglie predicted experimentally that if an electron beam undergoes diffraction, that is a characteristic of a wave, diffraction. So that utilizes these with the help of the this diffraction phenomena utilizes the wave nature of light. That is the how the particles are moving in the light in the same plane. And this de Broglie assumed that every object in motion has a wave character. So if any object has some motion, it has a wave nature. The wavelength which is associated with the objects are very short and the wave properties cannot be determined. And the wavelengths which are associated with electrons and other subatomic particles were also determined.